Welcome back, ChemStars. It's our last Chapter 3 video. We're on page 9 looking at average atomic mass. So you've seen it on the periodic table a couple times, but on the periodic table there are two very important numbers given. We have learned the whole number is the number of protons. Number of protons, remember that's the atomic number, which equals your number of protons. And the decimal number is the average atomic mass. We'll abbreviate that AAM. That is the decimal number. So where did this number actually come from? And how is it related to the mass number? So atomic mass is defined as the weighted average mass of the atoms in a naturally occurring sample of the element. Believe it or not, you've actually done some weighted averages in your math class before now. We're going to go, though, and show you how it applies to chemistry. A weighted average reflects both the mass and the relative abundance of the isotopes as they occur in nature. So using our periodic table, we want to find the average mass of carbon, hydrogen, and gold. Looking for that average, that decimal number. So flip to your periodic table, looking for carbon, hydrogen, and gold. So here's carbon, 12.011. So carbon is 12.011. Hydrogen is up here, 1.008. And then gold, here's gold on your periodic table. It is right here, 196.967. So 196.967. So those are the weighted averages of each of those type. If you're using the periodic table I passed out in class, it might be rounded to less sig figs. I'll put those numbers down for you too. The one from class only goes to 2 decimal places. So here are your rounded average atomic masses. Either one's fine. Just the first one I wrote is more precise, has more sig figs in it. So what do those numbers actually mean? Those are measurements in AMU, atomic mass units. We talked about that a little bit before on the mass of a proton, but working with masses that are like times 10 to the negative 27th kilograms is just too crazy. So what scientists did, we came up with the AMU and have defined it as 1/12 the mass of carbon-12. That means it's approximately 1 proton. So 1 AMU is equal to the mass of 1 proton, which is also pretty much equal to the mass of 1 neutron. Close enough for us right now. So let's look at an example for copper, and that's going to show you how the mass number and the average atomic mass number are related. So we're going to scroll down a little bit here. So let's take a look at copper 63 first. So go to your periodic table, find copper. Copper is right here, 29 protons in the nucleus. That is what makes it copper. So copper 63 has 29 protons, as does copper 65. If it didn't, it wouldn't be copper. Okay, let's focus in on this other example over here. So copper 63, the mass number is 63. So how many neutrons does it have? We've got to take 29 plus some number, add those together, and we'll get 63. So how do you find what's missing? Use your calculator or do some quick mental math. It has 34 neutrons. Compare that to copper 65. They're telling you the mass number is 65. So how many neutrons are in that nucleus? Well, total things in the nucleus are 65. 29 plus some number must be 65. Use your calculator or do your mental math. There are 36 neutrons in the nucleus. So if I have copper 63 and I have copper 65, in the nucleus of each, there are 29 protons. That is what makes it copper. But copper 63 has 2 less neutrons in the nucleus, and it's a little bit lighter than copper 65. So both of these are isotopes, our new vocab word, isotopes of copper, and they both occur in nature. However, if we take a sample of 100 random copper atoms from nature, you're going to find that every 69 of those have a mass of 63, and every, let's say 31 of those have a mass of 65. Or 69% of all copper is copper 63, and 31% of copper is copper 65. Now, if you actually Google that, you don't get a nice round number. It's like 69.2 and 30.8. I round it to make it easier for the problem. And if you add those together, you get 100%. So of all the types of copper in nature, they all have 29 protons. Look at this little picture here. Since they're neutral, they have 29 electrons, but what's different is the neutrons in the nucleus. Which one is the most common? Copper 63 is. And let's look at the weighted average on the periodic table. So on the periodic table, it says that copper's weighted average is 63.54. So according to your periodic table, it's 63.54. And if you can see, the one that has the higher percent abundance, the average atomic mass will be much closer than that. So 63.5 is closer to 63 than it is to 65. So that's the background in the theory. Now we're going to actually show you how to put all these pieces together. So here's our next I can statement, and also a really important equation that we'll give you for the test. So here it is. I can use percent abundance data. Oh, let's see. Highlighter's not working. I can use percent abundance data to calculate the average atomic mass of an isotope of a specific element. So like I showed you, elements come in a variety of isotopes. They're made up of atoms with the same atomic number, so same atomic number, but different atomic masses. These atoms differ in the number of neutrons. The average atomic mass is the weighted average of the isotopes of that element. So here's your important equation. That average atomic mass, that is what is printed on the periodic table. So this is your decimal on the periodic table. It is equal to the relative abundance times the mass number of one isotope plus the relative abundance times the mass number of a second isotope, and you can go on and add more terms. So what we're doing is we're taking how often it occurs in nature times its mass, multiplying those and adding them up for each isotope. To really understand this equation, we need to do some example problems. So flip to page 10. Okay, let's go through this first example problem. The relative abundance will always be given to you as a percent. The first and most important thing is that we need to take that percent and make it into a decimal. You do this all the time when you're looking at like sales or coupons and things like that. So for example, if it's 34.5%, that means it's 34.5 literally percent per 100. Take that percentage, divide it by 100, and this right here is decimal equivalent. That should be a review from math class for you. So you can either, so we're dividing by 100, we can either actually type this into your calculator, divide it by 100, or you can move the decimal places, 2 places to the left. So this will be 0.456, oops, 456. This will be, now be careful on these small ones, 1, 2. That means I got to put a 0 in, so 0.0145. This one right here, you can do that using moving decimal over, or if it gets really small, don't be afraid to use your calculator. So we got to go 1, 2 places to the left, 0.00887. So make sure you're comfortable converting those percents to a decimal. One thing to be careful of, don't press that percent button on your calculator. Sometimes that's pre-programmed to do different things. Make sure you either move decimal by hand or actually divide it by 100. Now that we have that out of the way, let's look at our first example. So we're going to be determining what the average atomic mass of cesium is. So here's the data we have. I'm going to try and color code it for you here. So 75% is cesium-133. So this is abundance 1, and this is the mass 1. 20% is cesium-132. That's abundance 2, that's mass 2. And then 5% is cesium-134. That's abundance 3 and mass 3. Looking at all those, the first thing you might want to check is, do those add up to 100%? Am I calculating everything here? So let's see, 75 plus 20 is 95, plus 5, that's 100%. Good. That means that I'm accounting for all isotopes. So my copper example, there was only 2 isotopes. On our cesium, now there's 3 different isotopes that make it up. So let's look at how that equation applies. I'm going to color code it here for you. So 75% is cesium-133. So to get from 75%, right here, we have to divide by 100. So 0.75 times 133 gives us 99.75. Then we've got to take the next isotope. 20% divide by 100, that's how we get to the 0.2 divided by 100, times 132, that gives us 26.4. And our last one, here we've got 5% divide by 100, that gives us 0.05, times 134, gives us 6.7. So these are the weighted averages of each isotope. When I add those together, take a second right now, try it on your calculator if you don't believe me. You're going to get 132.85 AMU. That is the weighted average. Now, no one cesium atom has this mass. But it's a really useful number for us because it is the weighted average of all the cesium. So if we go to the periodic table, let's find cesium. So cesium is right here. And look at the periodic table, 132.905. Let's see and check our work. 132, we were close, 132.85. Now, why didn't I get the exact same number? Well, there's a lot more sig figs on my periodic table, and there's actually a lot more than 3 isotopes of cesium. These are the 3 most common, and we've rounded it up, but we were within, a few hundredths. That means we did a good job. So here's a quick double check I want you to do every single time. Note, the answer should be between 132 and 134. Why? Well, because if you look at my initial data, the smallest isotope was 132 and the biggest isotope was 134. If we did a straight average, it would be 133. We're doing a weighted average, but it still has to be between my lowest and my highest number. The second check is that it should be closest to the highest percentage. So if you look at our numbers, it should be closest to 133. So did that check out? Is my final answer between 132 and 134? Yes. Is my final answer closer to 133 than any other number? Yes. That means that we've gone ahead and done it correctly. Okay, so I want to pause the video here. We've got several more example problems, but I think we'll have to split it up. So try the next 2 problems on your own. So right below this on the page. And then in our next video, I'm going to go over the solutions for those.